Welcome to Lesson 59. In this lesson, we're going to revisit calculus and see how calculus can be used to solve optimization problems in the areas of measurements, say optimizing area and volume, and also look at a speed or kinematics problem. You are going to work out investigation 23 in your textbook. When you have finished the questions, we're going to take up the questions in the first part of the video. You're then going to find parts 2, 3, and 4 to the examples in lesson 59 in separate videos because I want you to be able to try some of these questions on your own before looking at the answers. So pause the video now, work on investigation 23 before you come back to the solutions. Okay, so now I'm assuming that you have tried investigation 23, and let's take a look at how this can be done. So soft drinks are often packaged in cylindrical cans made from aluminum. The standard volume of such a can is 330 ml. This may vary among countries. Companies are always interested in minimizing production cost in order to maximize profits. Are companies using the least amount of aluminum in order to produce the 330 milliliter cans? Your task is to find the height and diameter of a 330 ml can that will minimize the can's surface area. Number 1. Write down an expression for the surface area A of a cylinder in terms of the radius and height. This expression should contain two variables. Which variables are these? For questions like this, I always begin by drawing a diagram and labeling the important dimensions on it. So we know that we're actually dealing with a cylindrical can. And this can holds a volume of 330 milliliters or cubic centimeters. And then they have mentioned the area, the surface area, and also the radius of this can, as well as the height of this can. In number 1, we want to express the area using height and the radius. So we have the two circle tops, 2 pi r squared, plus the body, so 2 pi r, which is the circumference, and then multiplied by the height, right? So here's A. Number 2, write down an expression containing the same two variables as used in question 1 for the volume V of a cylinder. Equate your expression to 330 centimeters cubed, since the volume of a drink can must be 330 cubic centimeters. So we know that the volume is pi r squared h, which after we sub in 330 turns into this expression. Number 3, use the expression for V from question 2 to rewrite the expression for A in terms of R only and state a reasonable domain for R. Because we want to write the area in terms of the radius, that means we need to find a substitution for h, the height. Using the equation from 2, I can rearrange it to show that h is 330 divided by pi r squared. And then let's substitute this into the expression in number 1. So we have A is equal to 2 pi r squared plus 2 pi r times 330 over pi r squared. And then we can simplify this and say that the function of A in terms of r is 2 pi r squared plus 330 times 2, 660. Pi cancels, r and r squared. Cancel one of them, you get 660 over r. And right away, I know that r cannot be 0, and because we're talking about dimensions, r should be greater than 0, should only be positive. Okay, number 4. Differentiate your expression for a with respect to r. Hence, find the values of r and h, which minimize the surface area of the can, and find the surface area in this case. Now, how does finding maximum or minimum surface area relate to differentiation, if you think about that? Well, back in year 1, we learned that the first derivative allows you to find the gradient of any curve, and at either maximum or minimum point, what happens? We know that something in common occurs at these points for which the first derivative of the function is equal to 0. Okay, so let's find the derivative of the last expression that we have. So differentiating a with respect to r, I get 4 pi r minus 660 over r squared. And then we set the derivative to 0 and try to solve for r. So let's see what we've got here. We have 4 pi r minus 660 over r squared. And then since there's only one single term, I don't have to worry too much about the r's. I can actually bring this over. R squared. Continuing on the side here, then I have r equals 660 over 4 pi, and then cube root. Okay. So now I have r approximately equal to, the squiggly doesn't show up, so let me fix it, 3.74 centimeters. If I substitute this back into the expression we found for h in terms of r, then we're going to get the height to be approximately 7.49 centimeters and a minimum surface area, which is approximately equal to 264 centimeters squared. Okay, and all of these answers are rounded to 3 significant figures. So hopefully you were able to graph the equation in here, and then notice you get the same result on the graph. So we say that optimization in calculus uses mathematical models to find largest and least value solutions to real-life problems. For number 7 and 8, you can discuss it with your classmates.